According to temperature readings taken from below, something is blocking the flow between Solz's second and third wells.
Might be something like a barrier between the two wells, which has not yet been opened by fracturing.
If they can't connect the wells, Solz will produce 50% less power than hoped, an outcome that could damage the future of EGS technology. They need to see what is stopping the water flow deep below.
We are presently trying to investigate the underground in a new seismic experiment, which is actually taking place presently in the background.
There's only one tool for the job, a seismic sensor called a geophone.
It's good.
One of the things you really have to understand is you are standing here on the surface and everything you are doing is 5 kilometers away from you. It's always relying on indirect information.
An engineer cranks open the wellhead. They start the winch and begin the long process of lowering the geophones to the blocked area. They're the same tools used by the oil and gas industries. But they often can't withstand the harsh conditions inside geothermal wells. Meanwhile, another technician places 2 massive machines into position. One 5 kilometers north of the well, the other 5 kilometers south. Weighing in at 22,000 kilos, they are known as thumper trucks. They work hand in hand with the geophones by sending large shock waves through the earth and into the blocked area of the well. The geophones, which act something like a sonogram, should record the shock waves and create a seismic profile of the blockage.
We are trying to get an idea about the geology and the structures of the fractures.
The geophones are finally in position nearly 5 kilometers below.
Okay.
It's time for the first reading. The geophysicist remotely activates the thumper trucks.
Can I show you how much it vibrates?
After a 1-minute blast, nothing. The geophone is not working. The hostile environment of a deep EGS well has once again taken its toll.
It fails due to the high temperature. The tool stays for 3 or 4 hours at about 180 degrees C. So the electronics then died.
To solve the mystery of the non-functioning reservoir, the team must now repair the geophone and start over again.
Here we have problems like this every day. Nothing seems to work in this well.
For months, in an attempt to increase power, the Solz team tried unsuccessfully to connect the 2 wells by injecting high-pressure water into the reservoir. The process failed, but it did cause another little-known side effect associated with EGS drilling: earthquakes.
We're talking about things which can disturb a population.
Over the years, the Solz project caused thousands of tiny, yet real seismic events. They typically occur when high-pressure water enters fractures in a fault line and acts as a lubricant. If EGS drilling takes place near fault lines, similar to those at the geysers in California, earthquakes are a possibility. The problem doesn't only affect geothermal drillers.
This is a known fact. Oil and gas industry has the same problems we have here at these depths.
In 2006, one of the largest earthquakes ever caused by geothermal drilling took place 190 kilometers from Solz.
We had in Basel a sister project. They're trying to do the same what we're doing in Solz here in 5 kilometers depth. They had a 3.4 magnitude earthquake, which caused people on the surface to be frightened.
It's improbable that EGS tremors will cause real damage, but the process must be monitored carefully. Hours later, the geophone is repaired. The team once again lowers it into position.
4,680 meters.
They fire up the thumper trucks. This time, the geophysicist registers a reading. The geophone is working.
From all this recording, we can use that part, which is usable.
The images show no openings between the two wells, but nothing about what is blocking them. The finding only deepens the mystery of the blocked wells. Unless they find a solution in the future, only 2 of the 3 wells will connect, and the power output of the plant will remain limited. But more importantly, any failure at Solz could dampen enthusiasm for future EGS projects. The Solz project may never get all the power they hoped from their experimental wells. But they have proven that geothermal plants may now be possible on an additional 50 to 60% of the Earth's surface. Australia and Germany are already building EGS facilities, based in part on Solz's research. Today's old-world drilling technology may be too slow to dig deep enough holes to make EGS cost-effective. But what if someone invented a drill that could cut through solid granite like butter and surpass depths of 15 kilometers? If such a technology existed, engineers could dig deeper, hotter wells at a fraction of the cost of traditional drills.
It's been a one-man operation here.
Some believe such an invention exists here, in this small, little-known laboratory hidden in a Northern California warehouse. In a few moments, Jared Potter, the general manager of Potter Drilling, will attempt what many consider impossible. Drill a hole in a half-ton chunk of granite in a matter of minutes.
This is really hard rock. You can imagine trying to drill that with any other technology is going to take a long time and going to take a lot of bits. So. Oh, whoops. Hey, Jim, it came off.
We need Allen wrenches.
Jared and a small team of engineers and scientists assemble an unassuming piece of equipment.
All right, here we go again, huh?
They claim that this metal cone will somehow bore a hole without any digging or grinding. They call it the flame jet drill. The drill was first conceived over 30 years ago by Jared's father, Robert Potter, a pioneer in geothermal science at the Los Alamos National Laboratory in the 1970s. Now, Jared has completed several prototypes designed to put the technology to its ultimate test. If the flame jet drill succeeds, it could be the holy grail for geothermal technology and one of the keys to lessening our dependence on fossil fuels.
This technology could drill as fast as 100 feet an hour, we believe, 10 times faster than conventional drilling. And since you're not contacting the rock, you're not wearing out the bit.
However, Potter must first prove his prototype works. Everything is in place for the test. Hydrogen gas feeds into the drill head. Once lit, it must reach 1800 degrees Celsius, hotter than lava. A barely visible, high-velocity flame shoots out of the drill tip, superheating the block of granite. Soon, tiny rock fragments begin flying off into the air. The intense flame causes flaws in the mineral structure to break down. The test is complete.
The entrance of the hole is about 4 inches, a little under 4 inches, and the hole itself now is about nearly 10